Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. In the next part, we're going to look at the significance of fluid mechanics. It is extremely important for engineers to understand fluid mechanics because there are a lot of engineering applications which involve fluid mechanics. For example, if you looked at in buildings, so we have the water distribution network, the ventilation systems, the air conditioning system, the firefighting systems. These are make use of fluids, which is the transport of fluids from one point to the next. And then if you look at the building envelopes, engineers also need to make sure that the building can withstand the forces due to the wind. So we need to also consider the effect of fluids on building. In a car, outside part of the car, we need to consider the aerodynamics of the car. And inside of the car, there are various systems which make use of fluids in hydraulic brake, in fuel flow, in the engines itself, the cooling system, the suspension, the shock absorber, all make use of fluids. In aircraft, of course, we need to consider the aerodynamic, what actually that cause aircraft to be able to fly in the propulsions, the jet engines, the gas turbine itself. These are all related to fluids. And then even in the environments, we have the switch systems, the drainage systems, the coastal currents, the pollutant flow in the atmosphere, even the weather systems. These are all related to fluid mechanics. Let's look at an example of a case whereby fluid behavior was not adequately taken into account by engineers when designing an engineering structure. In the 1940s, there is a bridge which is called the Tacoma Narrow Bridge, which actually collapsed only after 6 months after it was completed. It's due to the effect of the wind that gave rise to a phenomenon which is called the von Karman vortex streets, which give rise to oscillations of the bridge girder. And it just happens that these oscillations coincide with the natural frequency of the bridge. And because of that, we have resonance and then the bridge just collapsed. So let's watch a video of this very unfortunate case.
Perhaps, among other things, the Tacoma Narrows Bridge was the most spectacular aeolian harp in history. Unfortunately, its first performance was destined to run only about 4 months. In the meantime, she was a beautiful bridge. Beautiful, but a little strange. Even before construction was completed, people observed its peculiar behavior. That was because, even in a light breeze, ripples ran along the bridge. After a while, one of the local humorists called her Galloping Gertie. And for fairly obvious reasons, the name stuck, at least until the 7th of November, 1940. Then as now, Seattle and Tacoma were sports-minded cities. For 4 months, a regional sport was to drive across the bridge on a windy day. While some claimed it was like riding a roller coaster, others found it a little disconcerting to see the car in front disappear. How popular this bridge sport was, or to what extent it might have spread across the country, is anybody's guess. On November 7th, 1940, the winds were relatively moderate, about 40 miles per hour. A new mode appeared. Rather than ripple, the bridge began to twist.
It's vibrating and
A
twisting
wind of 40
violently.
miles per hour is not too strong, but it was strong enough to start the bridge twisting violently. And at 11 a.m., it fell. Investigators were mystified. A bridge constructed according to the best engineering standards of the day, perhaps the best bridge in the world. This was not a bridge that was supposed to collapse. What in the world had happened? Theodore von Karman, a Caltech professor and a pioneer in modern aerodynamics, came forth with the answer. Von Karman's explanation of vortex shedding and resonant oscillations was not universally popular among construction engineers. However, as verified by wind tunnel tests at Caltech and at the University of Washington, von Karman's explanation.
So from the video just now, we can see the effect of not fully understanding the behavior of fluids. So what actually happened when the wind blow past the bridge, there will be a formations of what is called a vortex or vortex shading, which we call the von Karman vortex thread. So as shown in this animation here. So the alternate shading of the vortices will cause the lateral movements of the bridge girdle. And then it just happens that the frequency of these oscillations, which was created due to the shading of the von Karman vortex thread, coincide with the natural frequency of the bridge, the creations of resonance. So the amplitude of oscillation continue to increase until the bridge failed. Now let us briefly look at history of fluid mechanics. Because the early applications of fluids can be traced back to the ancient Egyptians, whereby they built the irrigation systems for the plantations of crops. And then the first ever equations or quantitative relationships was derived by Archimedes. That's about 250 BC. And this actually gives birth to what is called experimental fluid mechanics. It's basically fluid mechanics by try and error by observations. Until about 400 or 500 years ago, during the time of Newton, Euler, Bernoulli, Neville, and Stokes, the scientists during that time has derived the equations that actually govern how fluid behave. This equation is called Navier-Stokes equations. The applications of three law of conservation of nature, law of conservation of mass, law of conservation of momentum, and the law of conservation of energy to fluid particle. And by applying these equations to the fluid particle, we can derive the equations that govern how the fluid behaves. And this equation is called Navier-Stokes equations because it was derived by scientists called Neville and Stokes in the 17th and 18th centuries. After that, there are a lot of works related to attempt to solve these equations. Navier-Stokes equation is very complex because it involves a second-order partial nonlinear coupled differential equation, which until now there is no exact solutions. But if we apply certain simplifications, we can obtain, in some cases, exact solutions. A lot of mathematicians has tried to solve these equations. So this area is called the classical hydrodynamics. And then parallel to that, a lot of works also being done by engineers by making use of experiments and then observe the relationships between different parameters. This area is called the experimental hydraulics. And then only in the 20th century, early in the 1900s, a German scientist called Prandtl has come up with a theory which is called a boundary layer theory, which will combine the area of classical hydrodynamics, whereby the Navier-Stokes equations is simplified and solved by ignoring the effect of viscosity close to the wall. So Prandtl come up with a theory which is called boundary layer theory. And then in the 20th century also, there are a lot of works started to be done related to highly compressible flow, the area of gas dynamics, for example, by Raymond, Marc Laval, and all that.